Horatiu has the honor to be the first speaker after the banquet. So happy to have Horatiu Nastase. He will tell us about probing holographic dualities through Penrose limits and dual spin chains.
Thank you. So first, I'd like to add to the voices saying that it's a wonderful conference, and we hope there's another one coming. So yeah, today I'll tell you about ways to test holographic dualities using the Penrose limit, specifically by looking at dual spin chains and trying to understand about the corresponding relation to the gravity dual. And this is based on these two papers from last year. So I'll first tell you about one such application for the duality found by Guarino, Jafferis, and Varela. And we'll see that we take some Penrose limits and we try to understand the spin chains that appear. And then another application is for T-duals of the abelian and non-abelian kind of the standard ADS5 cross S5. And again, trying to understand the field theory and learn something about it. So the Penrose limit corresponds, as you know, to a large charge limit in the field theory. And the reason one takes the Penrose limit is because we obtain a PP wave where strings are calculable, so we can understand something about the corresponding operators at large charge in the field theory. And so I would like to use this idea to less symmetric and more complicated holographic dual pairs where perhaps we don't understand yet the duality well enough, so this will give a handle on it. So the two examples, as I said, will be this duality found by Guarino, Jafferis, and Varela, and the T-duals of the standard one. So this duality corresponds to a warped and squashed ADS4 cross S6, and on the other side, a three-dimensional n equal to superior Mills-Chern-Simons at some IR fixed point. And on the other hand, the T-duals of ADS5 cross S5 are situations where also we have less supersymmetry, at least for the gravitational background. In the abelian case, the dual field theory is known as conjecture, is a quiver field theory, and in the non-abelian case, it's a bit more complicated, it's also a quiver. You heard a little bit from Carlos Núñez's talk. And the interesting thing is we'll find spin chains in the Penrose limit, but we'll find some mismatch in conformal dimensions, which we can think should be fixable in the first case, not so much in the second. So something is not known, either about the actual field theory or about the duality itself. So I think that's why this is interesting. So the first duality that I'll consider is this one found by Guarino, Jafferis, and Varela, which corresponds to a gravity dual, which is kind of complicated, but it's of ADS4 times here an S6 that is squashed. We see a CP2 and two special directions, and there's a bunch of fluxes. As usual, if you quantize the charges in this gravitational background, we find a relation between the parameters of the solution and some integers. In this case, the integers are n and k, and then all the parameters are expressed in terms of them. And on the field theory side, we have an n equal to superior Mills-Chern-Simons theory with a chiral and a vector superfield. And there's a dimensional reduction of the superpotential of n equal 4 down to 2 plus 1. Corresponding action then is this Chern-Simons matter and superpotential type. And we find two contributions to the superpotential. One that is conformal, it's basically the reduction from 4 dimensions, and one that comes from supersymmetrizing the Chern-Simons term. So in the infrared, where we are interested for the gravity dual, the Superior-Mills piece of the action will be subleading to the Chern-Simons that I wrote here explicitly, so we will drop it. And moreover, the conformal term in the potential remains one that, while this non-conformal one has to be put to the vacuum. So putting it to the vacuum in the infrared means that phi I commutes with phi j, but since these are complex and matrix valued, that's still a non-trivial set of fields. We can understand this in a different way through modifying an explanation of Guyot and Yin, but I'll not say anything about that. So let's now consider the gravity dual side and take the Penrose limit. In general, the Penrose limit corresponds going to a close to a null geodesic in the background. And consider the geodesic being parameterized by some affine parameter lambda. So then the condition for obtaining this Penrose limit is, first of all, the geodesic to be null, and second, that there should be no acceleration perpendicular to the direction, which amounts to this Christoffel being 0, and moreover, if the direction is an isometry of the background, the condition becomes simply this. The condition to be an isometry is not necessary, but it's a simplification because in that case we can calculate things more easily. So if you look at the background that I described for you here, you see 3 isometries corresponding directions that I denoted by psi, sigma, and phi. And so the things that you can think of for null geodesic to take the Penrose limit in are, for instance, motion in psi, in sigma or phi, or perhaps some combination of them. Another thing I thought about was phi plus sigma. And then you start looking at each one case by case. So for the first motion, we find a corresponding PP wave, and the symmetries of this PP wave match the symmetries obtained in a large charge limit of the field theory. And then the Hamiltonian for the string quantized in the background, for the closed string quantized in the background, is given here. And then the Eigen Energies, when this contribution is small, this object is small, are given like this. So at leading term, 4 of the components have energy 1 and 4 have 1/2, and then there's a correction. You can then also repeat the exercise for another isometric direction, sigma, but then you get something more complicated with cosines and sines in here. And for the other one as well, also with cosines and sines. And any combination of them is actually equivalent to motion just in this first one, as we can see, as you can find. So the first, the motion in the first direction will be found to correspond to the quantization. So closed strings for motion in this direction would correspond to the quantization of usual spin chain operators. But another test of the duality that one can think of is to find open string, quantization of open string and corresponding field theory operators. And then, so if you put an open string attached to a D4 branes that wraps some cycle, then you find a certain complicated action. And in this action, among the 6 transverse directions of the string, 3 are hard to diagonalize, to find the eigenvalues. But 3 are simple, and their eigenvalues are independent on which direction we consider the PP wave in, either phi sigma or phi plus sigma. And we'll see that this has consequences that it means that it doesn't matter how the open string moves, we still find some sort of mismatch. All right, so let me now tell you about the field theory. So as I said, for the field theory, we have to consider scalars that commute, meaning phi with phi j. Phi with phi j dagger still don't commute. And then, so on top of this condition, we have an interacting Hamiltonian that comes from the conformal part of the superpotential. To define the spin chain corresponding to a closed string, we have to pick out one special direction that we'll call Z, and then define that delta minus J is equal to 0 for this direction Z, and then write down the possible objects in the field theory, Z, Z bar, the rest of the phi's, phi bar, A mu, and D mu, and calculate delta minus J for all of them. And we find that there's a unique object with delta minus J equal to 0 that defines the vacuum, as in the usual case, as in N equal 4 spam-Mills. It's written exactly in the same way. However, the oscillators in this case are trickier. Since phi j commute, one possibility is to have commutator of phi with phi bar. Another possibility would be a product phi j, like it happens for the ABJM case, but we find that neither of these works. They don't give the right dimensions. So the only possibility for oscillators that gives the right dimensions, at least for n equal to 0, is this phi and phi bar. The usual phi bar and dA. Just that also including Z bar this time, in a kind of unusual situation. So the oscillators are written in the usual way. And then the classical dimensions of for n equal to 0 match the PP wave results, meaning we have 4 oscillators with energy 1 and 4 with energy 1/2. Then we can calculate a bunch of Feynman diagrams that I will not write here, and calculate for each insertion of these kind of oscillators. The Feynman diagrams give some factor, momentum-dependent factor that is written here. And this momentum-dependent factor corresponds to, multiplies the usual log x times lambda squared in the Feynman diagram. And this is the contribution that gives the anomalous dimension. So then, matching the two sides, we find that the anomalous dimension, delta minus j, is given by the tree result plus this f times the lambda squared over 2. And now I will stop and say that in N equal 4 spam-Mills, in the standard case, there was no function. We have a maximal supersymmetry, and all the operators had the same dimension at strong and weak coupling. However, we know in ABJM, which has just 3/4 of maximal supersymmetry, there is one function that interpolates between the weak and strong couplings. And then what we see here is that for each kind of insertion, we have a different function, fi of lambda. And moreover, then at small coupling, fi of lambda times g of p is fi of p times lambda squared. And on top of things, on top of this, we find that that the matching is only valid at small p. If we try to consider the full p dependence of this, sine squared and so on, that doesn't seem to match. Considering this object at strong coupling, we see a certain dependence with lambda power 2/3. And so by matching the insertions of various operators between the strong and weak coupling, we see that at strong coupling, each of these f's goes like lambda to power 2/3 versus lambda squared at weak coupling. All right, so the conclusion is for the closed strings in this background, we find some matching. It's a little bit different than the usual. We have a function for each operator. But also there is some mismatch at large p, large so-called magnum momentum. But on the other hand, when trying to match open string on D branes, we find that even delta minus j at 0 magnum momentum doesn't seem to work out. This is related to the fact that I described for you that we have these three components for which, no matter in which direction we take the Penrose limit in, the open string has always the same eigen frequencies. So here it would be mu over root 2, and here mu over root 6. And these things don't match any field theory operators that we can think of. So already in this case, there's some puzzle. Perhaps we don't understand the field theory. Perhaps we don't understand well enough the duality. Now I move on to the second case that I want to consider, the abelian and non-abelian T-duals of ADS5 cross S5. In the abelian case, we make a T-duality on one of the S5 coordinates. We get this background. And then in this background, we have, again, three isometry directions. And we can consider Penrose limits in each of them separately. The first one, we get this PP wave. In the second one, we get something that doesn't look like a Brinkmann form PP wave, so we're still not sure exactly what that means. We have some ideas, but not very well defined. And in the third one, which should have been the one corresponding to closed strings, we see that we cannot, we find that we cannot have motion just in this direction. The motion just in this direction is pathological. We have to consider motion in psi and psi, so two of them together, with the relation between the two of them defined by a parameter j. And then from the null condition, from the condition that the Penrose limit gives a null geodesic, we find that this j has to be less than a half. But on the other hand, in order to have a non-tachyonic mode, we have to see that j must be greater than 1 over 2 root 2. So we have a range of j's for the ratio of the motion in the two isometry directions. And the corresponding PP wave is given here. We find, again, the closed string action in this and the eigenfrequencies. Similarly, we can treat the non-abelian T-dual case. Non-abelian T-duality roughly means a T-duality in three directions at once, the three directions being rotated by an SU2. One can consider in principle also other groups, but the standard example is SU2. And so by doing this non-abelian T-duality, we obtain this background, which has two isometries now, beta and psi, and we can find the Penrose limit for motion in both of them. So for one, we find this PP wave. And for the other one, we don't find any solution at all. But then we remember what happened in the abelian case, that we need also motion in an extra direction. This time is a direction that is a kind of corresponding to a radial type of direction, but in one of the S5 coordinates. And again, we find the same kind of constraint, that the parameter j that defines the ratio of the motion in the two directions is bounded both from below and from above. So it belongs to the same interval. And then we obtain a certain PP wave for this geodesic. Again, we can calculate the closed string action on the PP wave and the eigenfrequencies. The eigenfrequencies can be found response to the abelian T-dual case and strong coupling limit corresponding to truly non-abelian case. So now we try to match these results with the field theory results. First of all, we have to define the field theories. The field theories are quivers. In the abelian case, so for abelian T-duality, the quiver is just a bunch of nodes of SUN connected by lines. So we have n equal to SUSY at each node and a vector multiplied between each SUN nodes, adjacent SUN nodes. In a non-abelian case, the quiver is infinitely long. It has nodes with SUN, SU2n, SUKn, dot, dot, dot. And as Carlos Nunez said, this only would terminate if we find a completion of the background. Otherwise, this thing doesn't make sense. It's somewhat singular. The quiver dual to ADS5 cross S5 mod ZK and its Penrose limit was considered in 2002 by these people. So now we would like to consider the case T dual to that. So when we do that, we obtain that, so T duality in principle is a symmetry of string theory, so you might wonder that perhaps we don't get the same result. However, the limit, the field theory limit one obtains in our case is different than the one considered by these people before T-duality. So in our case, we find that G squared n over k goes like k, so it blows up, whereas in their case it was finite. All right, so and we also find that the string coupling is very small, so the PP waves are classical. And in the field theory, we find, from the quiver, we find the corresponding superpotential written here, and kinetic terms here. We find that the symmetries match the ones of the PP wave. And then we write the charge assignment for the various fields in the theory. And when we do that, we find operators that have a charge in one direction U1, but also in another U1, which goes well in hand with what we observed in the PP wave limit, that we had needed motion in two directions. So now, corresponding to these two directions, we have two U1s. However, the ratio of these two U1s is in this case, if we look at the charge assignment, is given. It's just 1. Whereas in in the field theory case, for some reason, we had an interval between 1/2 root 2 and 1/2. So that's a puzzle. We don't know what that means. If we look at the vacuum, at the field theory operator corresponding to the vacuum, it's really the T-dual to the one found by Muki et al. In 2002, which is now an operator that kind of wraps around the quiver, just like a string would wrap around the compact dimension. And we can find also a bunch of oscillators with energy 1, dA, WW bar, XX bar, given here in the usual manner. The only non-trivial thing is that now the momentum is the sum of, the total momentum is the sum of each n for each winding. And we can compute the Eigen energies. And we find that 4 of them corresponding to the oscillators dA match. They're given by energy 1. However, the other ones would also give energy 1, which contradicts what we see in the PP wave. And then we think, well, what's the meaning of this? Well, we remember that, in fact, now we are in the unlike the case considered by Muki et al. So after the T-duality, we have a limit where G squared n over k is infinite. That means that there's a bunch of other interactions that mix operators. So we know that the result is not correct anymore. We have to invent a new way of dealing with all of these Feynman diagrams that give infinite results. So we at least understand the mismatch now. In the non-abelian case, we find a sort of renormalization group flow in one of the directions, the direction of the T-duality. And this corresponds to kind of a flow in light cone time between u equal to 0 and u equal to infinity, and it seems to be generic to not just the case, the particular background that we consider, but to more generic Gayoto-Maldacena backgrounds. So we've tried to understand this a little bit, but we could come up with just hand wave explanations. So one possibility is that conformal symmetry is broken in the dual because of the winding modes of the string, and that gives rise to an RG flow. Or perhaps we can understand this a standard way when we consider quivers via the idea of deconstruction. And there seems to be we find some arguments for this. We find that Wilson loops show some deviation from conformal behavior, and that a PP wave of a different solution, of a Janner solution, has some similarities with the non-abelian case, which perhaps means we should understand it in the same way, but the conclusion is not yet clear. So to conclude, let me say that we use Penrose limits to probe difficult holographic theories, and in one case, the Guarino-Jafferis-Varela case, with the Penrose limit for closed strings matched the BMN sectors, but only to the leading order. And open strings don't seem to match at all. And in this case, we find several functions with Fi lambda for different operators that interpolates between weak and strong coupling. And we think this is due to a much lower supersymmetry. And in abelian and non-abelian T-dual case, the operators, the BMN type operators are clear, but the naive calculations don't match because there are very large Feynman diagrams that can be neglected. So as a moral of all of this, I think we can say that we can perhaps take the PP wave calculations as predictions for probing unknown field theory issues. All of this assuming, of course, that we understand the duality. Thank you.
We have time for questions. Any questions? Yes.
So can you imagine generalizing this to further examples, or what is your avenue where you would like to go in the future? I mean, you're finding more
Well,
examples?
I mean, sure. So the reason why I focused on these two cases is because we knew that there was some issue with the holographic duality, so we couldn't understand them. But in principle, any case involving, let's say, not even necessarily ADS, we considered here ADS, but any case involving a sufficient amount of supersymmetry that we can do something with it, but not too much so that we can know everything precisely, would be good to apply the same kind of ideas.
Any other question? I have a question. So in the case of the open strings that you say they don't match, I didn't fully understand the operators. Don't you expect to have, let's say, quarks and anti-quarks rather than trace, and because you have a D4 brane in the background? And that's how it worked in the usual case, in the n equals 4.
No, so these cases are, these cases, just a moment, let me see where it was. Right, so in these cases, the strings correspond to strings attached on some D branes that wrap some states. So there are no quarks per se at the endpoints. You just have to consider certain operators with open indices. However, the point I was making, so I didn't write here all the trials that we make. We tried various things, but the point is that all of the possible ideas. So by now there's a standard way of of writing these operators. So the only issue is which kind of fields you put in and which PP waves it corresponds to. However, these modes, they will never appear, because if you rescale this to be 1, so you just consider, let's say, mu equals square root 2, then this is 1 over square root 3. I mean, just saying that, it's enough, right? I mean, there's no way to obtain, as a classical dimension, 1 over square root 3, so.
I was meaning if you have a D4, then there are going to be open strings from the D4 to the D branes that mate in background. And then this by fundamentals giving you the quarks.
Sure. So okay. So this would be another type of situation of open string. So you can consider different kinds of open strings, right? You can even consider adding quarks to the field theory and so on. But the things we consider here is open strings in the base theory without quarks. And the way this is understood is via these D-brane probes in the dual gravity dual. So, yeah. In this case, there seems to be no way, because, well, 1 over root 3 is not an integer. So.
Okay. Any other question? Okay. So let's thank Horatiu again.